Alright, so I think we're getting to the point now where I keep my voice low. So I'll do that, and yeah, keep my voice low and the gain pretty high up on my voice low and the gain high on the microphone. So hello and welcome. We'll get into another problem. We'll just kind of get right into it. LeetCode medium integer break. Let's see how we do. Give it a positive integer n, break it into the sum of at least two positive integers and maximize the product of those integers. Return the maximum product you can get. Oh, wow. Okay. Interesting. That's a neat, nifty problem. May assume that n is not less than 2 and not larger than 58. So I think you can do this in square root time, and I believe it's going to be the product of sort of the most even divisors. And yeah, so let's take a look at a number. We'll just get like an example. So if you do like 100, right? 100 has 1 is divisor, 2 is divisor, 3 is not, 4 is, right? We'll do each of the pairs. 50 and 25. There's exactly square root of them, so it should be about 10 of them, and then pairs means there's only about 5 of them. Or, no, I'm sorry. 10 pairs. It should be about 10 pairs. 6, 7, 8, 9, 10. I don't think 6 is divisor, 7's not, 8 is not, 9 is not, and 10 is okay. So excuse me, it's not 10 pairs, but there are a small number of divisors. We'll just say yeah, it's roughly it's less than square root of n. It's less than 10. The pairs. So 100 when you no, these are the, I'm sorry, excuse me, I take it back. I'm wrong. All of these, I don't know, never mind. What I'm thinking is totally wrong. So it could be 1 in 99, 2 in 98, 3 in 97, right? To would be 48 and 52, 49 and 51, 50 and 50. Okay, so in this, what we're looking at here, there's exactly, it should be 100 over 2, half of, yeah, 50 pairs. Excuse me, and right, the numbers get sort of closer together. And what we want to do is take the multiplicand. So this is 99, this is 98 times 2, it's 196. This is, it's 300 minus 9, it's 291. And these are, this is 2500. This is, subtract 50 to give you 49 times 50, and then add another 49, gives you, subtract 50, and then 49, I think 2499, right? Yeah, and this is 48 times 52, we'll say that would be like adding 96, subtracting 100, adding 96, right? You can use some calculus, I think, for this problem. Yeah, so it looks like it would be roughly divided by 2. And we would want to say something like this. Something like this. Not less than 2 and not larger than 58. Really interesting. Not less than 2, okay. Let's see how we do. Wrong. Okay. Wait, what? You can get this number? I want to say you can use some calculus to figure this out. X plus y equals some k, and x times y equals some alpha. And we want to maximize alpha. So y would be k minus x. Alpha equals x times k minus x, which is negative x squared plus x times k. D alpha dx is then negative 2x plus k, which equals 0 when x equals k over 2. And we know that, so that's a, if we have a number line here, k over 2, the derivative is positive, right, when k over x is greater than k over 2, we would say it's actually less than 0, and it's positive when k is less than k over 2, when x is less than k over 2. And the second derivative is, of this function, is negative 2 with respect to x. So it's always negative. It's sort of alpha double prime. Alpha prime and alpha double prime, right? And we get alpha prime and alpha double prime, which means that this function looks like this. So if we want to maximize, the maximum is at exactly x equals k over 2. When this is alpha, and this is the function for alpha of x. So that's basically, you can use calculus to figure this out. I was thinking that's probably the case. And now the weird thing that's weird though is I don't think these numbers are right. Yeah, that's not correct. Even if these are integers, it's still, you know, this just becomes, you know, these just become integers. This is definitely not. I don't know, I'm so confused actually. I don't understand. How is it, maybe I misunderstood the problem? 10 gives you 36. Oh, you could have more than one integer. I'm sorry. At least 2 positive integers. Oh, so I take it back. Okay. Oh, actually, in that case, you want to. Oh, I see. All right, that's a very different question. I was going to say, I was like 58 seems like a really small number. 58 seems like a really small number for what we're doing here. Yeah, so, okay, I see what's going on. So, actually, in this case, you want to break it down into as many divisible parts as you can. Yeah, it would be Okay, let me see here. Pretty interesting question. Yeah, so I think this is wrong, by the way. Oh no, it's right. Oh, look at that. Okay, never mind. Alright. Huh. You can do this using dynamic programming. You can say, so I have an idea, we can do I'm going to memorize this function. Now we're going to say base case what we're going to do something like this. No. Yeah, that's what we want. X minus I is greater than or equal to 2. Now we're going to say F something like this. We take another number and we recurse, and we say we have a memoization too. Yeah, we'll do unordered map. We'll do it this way for now. There's probably another way we could do this. Okay, let's try something like this. And I did this wrong also. I do that wrong fairly often. Both of these I did wrong. We can actually use it, do this statically too, make this even more efficient, more faster. Static memoization. And yeah, we can use, since we know this is not going to be larger than 58, we can also memorize this in a special way as well. So yeah, dynamic programming, I think is a reasonable way to do this. What we would say is, okay, we have an optimal breakdown for, to give you the largest multiplicand that you can get. It's x. That's my mistake. For 3, we said no, this actually could be at least 2 positive integers. That's a little confusing. Three can be broken down into 2 and 1. I could be 1. I actually could be 1. I'm wrong about that. Yeah, I could be 1. It just has to be greater than or equal to 2. Yeah. Is that right? We get I could be 1. 3 minus 1 is 2. I could be 2. F of 2 is 1. It could be the value itself. Also, I want to say something like this works as well. Yeah. Let's go through all the numbers. All right. Let's do all of these, see how we do. Let's go for it. All right, we got there. Pretty good. Yeah, I mean, you can't really go faster than that, can you? So yeah, in some instances, the number itself is better. There's a way to do this that's more efficient. So we can do a vector instead of an unordered map. And it could be integers. And it could be of size n plus 1, 0. And we would do if pretty much none of them should be 0, I think. We'll just do, we can do it, let's not do it this way, let's do the size, check the size. That size is greater than x, oops. And we've already calculated it, so we want to, of 2 should be 1. Actually, no, we do want to go back to these 2. Yeah, so if the size is greater than x, or if x is less than memo size, then we can return that. And we're going to say for, yeah, we'll do I want to do dynamic programming in the other direction. So we would say oh yeah, this is linear time. This is really fast. We would want to do, how do you do this? It's for int I equals, really should be x. X. And x is greater than or equal to 2 minus x. And we'll say int j equals x minus I. This is a little confusing, I realize. And this j starts off at 1, right? Like it doesn't need to be, we could, I don't know, we could do it the other way around. I don't know. It's confusing. So, I don't really want to memorize this. Yeah, memorize is fine. Okay. All right, fine. Memorize directly of x of I, x minus I. It's not really recursive anymore either. I'm a little confused. So what we want to do is take the difference between the size of memo and the size of x. Right, and we're going to calculate each of these values, and for each of those values we're going to say, no, it's not linear, I'm sorry, it's not linear time. This is I believe this is quadratic. It's very fast because there's only 58 numbers to go through. Yeah, I take that back, it's not linear because there's a lot of numbers to go through here. Oh, maybe it is linear. Well, I don't know. Each of these would be constant time once they've been memoized. So, yeah. I think it would be linear, still would be linear if you memorize it. So for j equals 0, let's start off at j equals memo.size minus 1, and j is less than or equal to x, increment j, you're going to say int next val equals 0, or yeah, we'll do ret. Ret equals 0, we're going to say ret equals standard max, we'll do memo dot pushback ret. And then for memo of X. Yeah, something like this. What does this do? Does this even compile? Nice runtime error, okay. Yeah, this is a little confusing. So X is 5. I don't think you need X is 5, let's say memo is 3. So 0, 1, 2, 3. Or the size is 3. 3 means we have 0, 1, 2. So the size is always 1 above what you actually have. So we need to go from 2 to 5. We need to increase the size to 6. So we actually want to be at X plus 1. Something like this. And what we're going to do, these are fine, I think. We assume in this loop that we have all the values for memo that we need. It's not X minus I, it's J. Yeah, okay, that's the thing. It's got to be a J, not X. Excuse me. And so now it's J instead of, yeah. And what we want to do is, so memo size is 3, and let's say X is 5. We want to go to 2 more values, right? 3, 4, 5, and 6. Or else 3 more values we want to add. Yeah, 3, 4, 5, and 6. Is this what we need? Hold on. Let's see what happens if we do this now. Okay. Overflow. Whoa. Oh, right, because we're looking at huge numbers now. Really? So these end up being gigantic numbers, huh? This kind of shouldn't be that difficult, this part. Let's go to just 10. Let's just try 10, see what happens. Get the right answer. Okay. 20. Oh, it's still correct. Okay. 40. Okay. How about 50? Oh. Okay, what about 58? Runtime error. Really? How come we don't run into that runtime error before? somehow 58 is, oh wow. 2 times this number cannot be represented in a type integer. Really? Huh. What is this? A surprise? It's kind of weird. Okay. Let's go for it. Still 0 milliseconds, however. Yeah, interesting. We really don't need to recurse anymore, do we? With this. Actually, we do want to. If it's a negative number, we still want to return 1. Whoa, 4 milliseconds now. Okay. Still 100%, but what we can do now is make this static. And let's see if that's faster. Yeah, that'll work between calls. The thing that's so weird about this is we make these integers, and it's really bizarre. We run into a problem. And the reason is, yeah, right here we have this signed integer overflow. Now how did that happen? 116.226.1967 times 2. And 2 raised to the 31st. Divided by 2. Yeah, that's 1,000 million billion, a billion. 1,000 million billion. Yeah, 1,000 million billion. So what's weird about this though is I don't know how we got this here. I guess that's 2 and j minus 2. Strangest thing. '56, memo of 56, right? I don't know how we ended up with 2 times this thing. Right? What do we get here? Oh. Yeah. Look at all these numbers, man. I'm so confused because it says that 2 times this thing won't even fit into an integer. However, this return value is an integer. So it's really confusing. Because I'm wondering to myself, how is this even possible? How is this even possible? Now if we make these longs, yeah, I'm just totally confused. I want to say there's some kind of an overflow that's happening. It's causing issues. No, this is still the right number. But somehow... What number do we get at the end here? This thing. Whoa. What's this one? Divided by 2. Huh. Yeah. Interesting. I'm so confused Apparently this is what got chosen, this memo value times 2. This was the winner. But why wouldn't 4 times this guy be the winner? Oh no, that's why. It's because it's 3 times this. Which is smaller. I am the most confused. Which is smaller than this number. Oh no. 3 times that's fine. That's the same number. 15496819556. How about this one? Oh, they're all the same numbers. Huh? Oh, that is so confusing. What? What is going on? I am just utterly confused. I do not get it at all. Huh? What is going on, man? Oh, it's too big. That's why. That's why. Oh, that is so confusing. Yeah. Brother. Brother. How did I get that wrong? I don't know. How did we get that wrong? It's wrong, he's just so wrong. Okay. Okay. Yeah. So yes, this should be basically a lot more efficient. This will be static, and it'll be constant for values that we've already gone through. So the first time you do 58, what do you get? 0 milliseconds. Okay, sweet. So, oh, that's pretty good. All right. I just wanted to make sure, like, I understood how you can do this in a way that's not just memoized, but also memoized across multiple calls, multiple test cases. I don't think this is linear time though. It's kind of like linear. I don't know. It's kind of hard to tell. Excuse me. As you saw, there were a lot of calls that were made. I want to say it's quadratic. I really don't know. Let me see what the discussion says. See if we can find something that's faster than quadratic. Because for this problem, it kind of is fine to do. It's kind of fine to do this in. I really do think if I did the recursive version that was memoized, I think that's linear. I think this version is not actually linear. And the reason is I really don't know. I have no idea. I want to say that like each of these are linear calls, even though this really does look like quadratic. You know, it's sort of a double for loop. I think it is quadratic. It's just no, I think even the other memoized recursive version is quadratic. I really can't tell. Linear solution. Logarithmic time solution. Constant time solution. I don't know, man. Linear solution with DP. Explanation Chinese. Okay. I don't know. I didn't really think too hard about this. About this one. Factors of 2 and 3. Yeah, so actually, right, that's another part is, as you noticed, this question really isn't that interesting beyond, yeah, okay, so, all right. So this approach is fast, but it's also not as efficient as it could be. So something you'll notice is basically you have 2s and 3s. Like I said before, if you look at 10, I thought 2 raised to the 5th would be better than 36. But if you go to 12, 2 raised to the 6th should be better than really anything else you can get for 12. And if you look at 12, you can see that. Oh no, I'm wrong. Sorry. 3 to the 4th is still better. Alright, you gotta go after there's a certain point where you're better off with using 2 raised to a power than you are using 3 raised to a power. When do they pass each other? 3 raised to the 5th is like 15. 2 raised to the 7th. 3 raised to the 6th is 18. 2 raised to the 9th, I think is when they pass each other, yeah. 18. No. 2 raised to the 9th is still, yeah. How about like 20? 20 is 2 raised to the 10th, which is 1,000, and let's do 3 raised to the 6th times 2. No. How about 25, or yeah, divisible by 3. Factors of 6, so 24, 30. Let's try 30, okay. 2 raised to the 15th, and 30 is 3 raised to the 10th. Okay. 59,000 compared to 30,000. No, 3 is still better. 3 beats 2 for a while. There's some multiple of 6. Let's say, let's do like 60. Okay. 2 raised to the 30th. Oh, 60 is pretty large, actually. 60 is actually beyond the numbers we're even interested in. So really it doesn't matter. And then we would say, 3 raised to the 20th. Right, that gives you 2 raised to the 30th, 3 raised to the 20th. Oh, 3 is still better. 3 seems to dominate 2 all the way. Let's go to like 120. 2 raised to the 60th. Compared to 3 raised to the 40th. So that's like 12, 1, 2, 3, 4, 5, 6. 12 is 6, it's 1, 2, 3, 4, 5, 6. 3 is beating even to 120. Why is 3 so much stronger than 2? It's not like that forever. There's some, alright, we're gonna have to do some maths here. Alright, you ready? 2 raised to the x, 3 raised to the y. 2 times x equals 3 times y. Right? Equals k. Find the first k such that 2 raised to the x is greater than 3 raised to the y. Alright, that means natural log of 2 is greater than natural y, natural log of 3. That means that x is greater than y times the natural log of 3 over the natural log of 2. And x is also equal to 3y over 2. Or alternatively, we'll say y equals 2x over 3. Which is to say that x is greater than 2 or 3x times natural log of 3 over natural log of 2. Which is that 1 is greater than 2/3 natural log of 3 over the natural log of 2. Which I think is never true, actually. So I'm wrong in my hypothesis here. I could do regular log also, it works fine. Times 2 divided by 3. Oh. So yeah, no, this is always smaller, 2 raised to the x. Oh. Okay, so you never pick 2. So always pick 3. Now about 3 and 4. 3 raised to the x and is less than 4 raised to the y. 3 times x equals 4 times y equals k. And that means that x log 3, so x is less than y log 4 over log 3. And here we have y is 3x over 4, which gives us 1 is less than 3 over 4, log 4 over log 3. So, which is also never true. It's a 0.9 ... So this is always larger than 4 raised to the y, and basically any other value of y that you could pick, or value of any other base you could pick, would increase here more than we increase up here. So that's why 3 is really the one you always choose. It's a simple explanation for why you basically just always pick 3. And what you're going to do is pretty much, you can actually do the math then from there. So you can say if x is less than or equal to 2, turn 1. And now you're going to say x, or we could change this back to n. You're going to want to use 3s, so you're going to say int ret equals 0. We're going to do it's n divided by 3. That's the number of times you can break this into 3s. It's n divided by 3. It's 3 raised to that power. Right, that's an integer. So 3 raised to this power. And then whatever you have left over, n minus equals 3 times n over 3, or in other words, n modulo 3, should give you a 1. You have a few options. You could have a 0. You have 3 options for any, so switch on n modulo 3, case 1, or case 0, turn ret. All these cases return ret. Just break. Case 1 and case 2. We have 3 possibilities. Right? If it's math or C math or something. I forget what it is. Nice. So if we have case 1, we're going to do ret times equals 4. If it's case 2, times equals 2. Something like this. 13, 11. Wrong. So what's going to happen is 12 we have 3 4 times. 11 is correct. 11 is we have, oh, let's go back to 10 also. Does it work for 10? 10 we get 108. Nice. Nice. Oh, I see. So, no. Okay. So what happens for 10 is we've got to divide by 3 and then multiply by 4. Something like this. No. What? What is going on? Did something wrong. Let's go back to 9. So 9 is 0. 9 is 0. We do 3 plus 3 plus 3. 10, we have 3 plus 3 plus 4. So we would divide by 3 and multiply by 4. In this case, upgrade one of the 3's to a 4. Because you have 3 times 3 times 1, which is only 9, 3 raised to the third. You actually want 3 times 3 and then times 4, which is better than 3 times 3 times 3 times 1. When you have modulo 2, on the other hand, so it's 9, 10 has a 1, 11 has 2. You multiply by 2 because you're going to basically multiply by all 3's, and then you're going to multiply by a 2 at the end. So something like this. There we go. Okay, let's give that a shot. Oh! No, we got it wrong. I didn't test enough. I didn't think to test enough. Got a wrong answer. Oof. What are the wrong ones? Let's go on the diff here. 3 and 2. That's the only one. That's when it's 3. Oh no. 3 is the only one that should be 2. I think that's the only case that's different. Everything else should be the same. Yeah, should be correct. Wow. Still a lot of memory being used. It's kind of surprising. So this is basically a constant time solution. And yeah, I don't know what to say. You do else, if, you know, for these. Pretty interesting question. Don't need this gigantic switch statement. Too much memory being used. How about that? I mean, you can't really go faster, but maybe we can use less memory. Somehow use less memory. Let's do n-1. What about 0? I get the wrong answer. That's funny. Yeah. I don't know, man. What if we just do this? What do we get? Wrong answers everywhere. So what if we get -1? Invalid test case. So 0 is a valid test case, though. That's kind of interesting. Yeah, I don't know. How do we... n is less than or equal to 2, we would do 1. We just do else if n equals 3. Turn 2. And yeah, our rules don't really apply. Right, because if it's 3, then we get 3 raised to the first, which then that would just be it. It would just be 3. It would be 3, which is wrong. I don't know. I don't know how to get the less memory usage. I don't know how to do that. I don't know how. Yeah, How do people use less memory? How do they do that? Oh, wait, this one had very little memory usage. How did these have less memory usage than... I'm so confused. $57. 5.7 megabytes. How? What? There's no way. There's no way. How do you use less memory? So yeah, this is obviously effectively constant time. I mean, this function's not exactly constant, but that's pretty much how you do it, is that, you know, the threes kind of powers of 3 for this, these numbers overtake all the other powers sort of indefinitely. There's that, what do you call it, that function that I showed you over there where you can compare different possible powers that you might want to use. And basically in all cases you want to have threes, as many threes as you can get. Now the question is, okay, let's say, can we do int p equals, no. I don't know how to use less memory here. I have no idea. I don't know. It's kind of funny to me that this is like not always 100%. Something about that seems a little weird. I guess my other solution was really efficient too. I don't know, man. I think my other solution, because it was static, actually was just as efficient and used less memory, because I guess it's like amortized memory or something. I don't know. That doesn't seem right. It doesn't seem to make sense. I don't know how this uses more memory. I can't. It's definitely this power function. Let me do this in a loop. Let me do this in like a... The problem with computing powers directly is like, it's just kind of awkward. Alright, we're going to do a for loop. Let's get this power function out of there. Let's try that. We're going to do... How about this? What if we do this? Still the right answer? Is that more or less memory? Okay, that's a lot less memory. Okay, yeah, that's what I was thinking. There we go. 5.9. Come on, man. It's not as efficient though, you can see. It's too funny. How do we do this? There are ways to compute powers that are kind of interesting. So let's do this. Let's do int x equals n over 3. And then we want to say ret equals 3, right? That minus 1. And we're going to say ret times equals itself squares itself, right? Isn't that a weird looking line? While say I equals 1, I times I is less than n over 3. I times equals itself. Ret times equals itself. And then we'll do another routine over here, which is going to be int j equals 0. And just I plus j is less than n over 3, or is less than x increment j. Or another way of doing it, j equals x minus I, and j is greater than or equal to 0. This is a weird way of doing things, but technically would be a little more efficient than, I don't know, integer overflow. Nice. Awesome. Alright. Oh, it's I plus I, or 2I. How about that? Overflows. Basically, I want to square the 3 a bunch of times. Then we say 3 times 3 will give you 9. You're going to get a lot closer to x. You're going to get I. So you have 3 raised to some power, and that's ret. Call it alpha. And now you want to get 2 times alpha. I starts off at 1. Ret is 3. 2 should be fine. I multiplies by, it actually multiplies by 2, I think. This is really interesting. What number are we looking at here? I don't know. We go all the way down there. Why do I feel like this is not... These aren't the right answers, but it's definitely this one that's causing problems. Yeah, that's the wrong answer, but it's this thing that's causing issues. So this is sort of off by 1 over here. So this is x minus 1. Yeah. If we take, oh, it's not greater than or equal to 0, it's greater than 0. Nope, still too large. Let's just do this on a few smaller ones. Like 30, let's do like 30. Wrong answer, okay. I want to say this has got to be, oh, that's why, because I is, oh, that's why, of course. No, this is too big, right? There we go, that's what I thought. Okay, now the question is, okay, that's faster, uses a little bit less memory. No, not much. No, it's the same thing. It's basically the same thing. We didn't need to go through all that. Well, this is unnecessary. This doesn't really change it too much. This changes a little bit, but it doesn't change much. We could just say yeah. Okay, I guess. Just leave that as it is, I suppose. It's actually not as efficient as just doing this. But it does use less memory, which is kind of interesting. That's fun. Anyway, let me go. So yeah, that's a really interesting problem. I don't know, I like the math problems. It takes me a while, but yeah, here we go, 1 hour and 17 minutes on this, and it's kind of an easy question. I don't know, man. I like kind of just thinking about the different things you can do. So anyway, yeah, hopefully that makes sense. Thank you all for watching. Talk to you soon. Have a good rest of your day. And I hope that was interesting. Take care.